In this video, we'll give an introduction to linear systems. After studying this video, you should be able to identify examples of linear systems in engineering and science. And we'll note that those are very common. And become familiar with some vocabulary that we use to describe linear systems of equations. So how do you know an equation is linear? And this may be review for you. So recall the general equation of a line, y equals mx plus b, that you learned in algebra. We can write this as a linear combination of two variables where we have 1 times y minus m times x. It's called a linear combination because each variable is a constant times a variable. And the variable is not raised to any power, and it's not a function like a logarithm or a cosine or anything like that. Then if we generalize this, we might call y x1 and x x2 and generalize this to be a linear combination of any number of variables. We can write the general linear equation as a1x1 plus a2x2 plus all the way to some an xn equals b, and this is for some n variables. And when we have n variables, we'll have n constants. So an equation is linear if it can be written in this form, even if it is not initially presented in this form. You might be able to do some algebraic manipulations to get it in this form. So once we have an equation with n variables, we need at least the same number of linearly independent equations as we do unknowns if we're going to solve it. Okay? So what we really have is a system of n equations by n unknowns. So we'll talk about linear systems in terms of how many equations. So this is an n by n system. And we can label the constants in the equations with subscripts to identify first which equation, and second which variable that constant is a coefficient for. And again, I think I didn't introduce that term before. These constants are also called coefficients of each variable. A couple terms here. We have an undetermined system, not enough equations, if there's not enough equations. And then there's an infinite number of solutions. So this would be where our number of equations is less than our number of unknowns. And we actually do encounter this in optimization problems in engineering, where we have to pick the values of some of the variables and solve for the rest. We have an overdetermined system if we have more equations than unknowns. In other words, we have more equations, and they might be more linearly independent equations than we have unknowns. And we will see this actually in this class for curve fitting. It's pretty common. And we'll see more examples of that in the coming weeks. So let's get back to this idea of linear independence. A system is said to consist of linearly independent equations if no equation can be expressed as a linear combination of one or more others in the system. So here's some examples that are not linearly independent. So if we look at this first example, and you look at these two equations, you can see that equation 3 is equal to twice of equation 1. In other words, the coefficient for x1 is twice the coefficient of 1 here. The coefficient for x2 is twice the 2. The coefficient of 8 is twice the 4. And the constant on the right hand side, -2, is twice -1. So this would be, makes this system not linearly independent. Here's another example where we can see that looking at all of these equations together, the equation 3 is equal to equation 1 plus twice times equation 2. And what this means is that that third equation in both of these cases is giving us no new constraints on the system. So in all of these cases, the system is underdetermined. And we'll talk about some ways to figure that out when you can't do it by inspection in the future. So let's look at some examples of linear systems. One place we commonly see them is in structure analysis. Both trusses and frames. You might remember this in statics, if you took statics. Here's a bridge truss here. Another place we see them is in circuit analysis. Where applying Kirchhoff's laws, we end up with a linear system of equations for these 4 currents in this electric circuit. Chemical reaction stoichiometry. When we do an atom balance, we get a linear system of equations. And looking at this equation, this is the combustion of propane. And you could probably balance this equation by inspection, but when we get into more complex chemical reactions, especially in organic chemistry, we end up with cases where we actually do need to set up a linear system of equations and solve it. And then we'll commonly encounter linear systems in the context of numerical methods algorithms. And let's look at a couple examples here. Some of the places that we will encounter linear systems later in Engineering 240 include solving nonlinear systems, where we will basically convert a nonlinear system to a linear system to solve. Another area is curve fitting, and as I mentioned before, this is going to give us actually an overdetermined system for some algorithms. Interpolation. And interpolation actually gives us what we call an ill-conditioned system. And we'll talk about what that means in future videos. And finally, we will be using linear systems for finite difference methods for differential equations, where we replace differential equations with approximate linear algebraic equations. We'll see all that in the coming weeks. But first, we need to focus on how do we solve linear systems numerically.